Okay, let's take a look at the process of integration by substitution, and I want you to go ahead and play with the warm-up here to start the video. And as usual, we'll kind of get you the answers, and anything we talk about in the video that you need a little bit more clarification for, we'll talk about in class. So the first warm-up, remember it said try and go about it geometrically here. Use the graph, and you'll find basically you're finding the area of two different triangles, one a little bit below the x-axis and one above, and you should get a final answer of 24. So that'd be D. And then number 2, you really should be looking at this again at this point in the game as really something you have to expand. So you want to get yourself to the point where you're basically multiplying 8x through times this expanded polynomial here. I won't do all the tedious work here, but in the very end you should get basically 64 over 3 x to the 6th plus 16x to the 4th plus 4x squared, and then of course plus c. But this is a good lead-in to this substitution process that we're going to need to use sometimes. So as you flip the page here, let's talk a little bit about how this process works and what we do with it. So like you see, right, we're looking for some type of a pattern. So what if the problem we were working with was 4x squared plus 1, but to the 7th power, and then you have that 8x dx. And the reason I chose this is because I knew full well that obviously we're all smart enough to understand we wouldn't want to expand this to the 7th power. So as we look at some of the blanks here, what we want to do is we want to take special note of the idea that 8x happens to be there in the middle of this problem, and it's kind of not coincidental that 8x is the derivative specifically of 4x squared plus 1. And that's kind of like a happy coincidence. So one of the first bullet points you see on your notes says no need to panic. Do you notice that 8x, right, is a derivative? And then it says of the question mark, right? So it's a derivative of this quantity, right? That's being raised to the 7th power. So think of it that way. And here's what you want to do, and this is my helpful hint. You would like to, going forward, visualize the integrand, the part inside the integral, as, okay, you ready? The product, right? This is all the integrand here. This is the product of a differentiable power function and its derivative. I think this is kind of where we're going to be earning our money here as we try to integrate these things. So what does that mean for us? Well, I'm going to look at this, right? We're going to do this thing called u substitution. So we're going to say let u equal 4x squared plus 1. Notice not to the 7th power, just 4x squared plus 1. The derivative of this, du dx, is equal to 8x. Now watch this sleight of hand here, right? If I were to say du is equal to 8x dx, just by doing a little algebra there, right? Think about that. I'm just multiplying both sides by dx, right? Then that gets me to a situation where I could actually make some equivalent substitutions. So let's show you what that would look like, right? Let's go back to the original problem. Here's my original problem. 4x squared plus 1 to the 7th, right, times 8x dx. Take note of the fact that I could actually replace this with a u and this with a du. And now the only thing that's kind of not touched here is the 7, and so we are actually integrating a very similar problem. How much easier is it for us to integrate u to the 7th than it is all this jumbled mess that we started with in the beginning? So our answer then would be, what do I get when I integrate u to the 7th? Well, you get u to the 8th over 8 plus c. How does that translate? Well, that gives us a final integral answer, right, of 4x squared plus 1 to the 8th over 8 plus c. And that is the process of integration by substitution. So I'll show you two more examples to kind of get you a little bit more comfortable with the process, and then we'll let you practice a couple on your own, get you some answers like we usually do. So let's look at examples 1 and example 2. Right? So here's example 1, right? The integral 2x minus 3 to the third times 2 dx, right? So when you're looking for u, as we said earlier, right, you'd like to pick the function being raised to the power. So in this case, we're going to do 2x minus 3. That then allows you to say du would equal 2. And I'm going to, again, one more time, dx, du dx is the notation, right? I'm going to swing this over here so that I can just write du as 2 dx. This allows me to substitute u in here, du in there, and really what I'm doing is I'm creating a modified version of this problem, much easier version, and I'm integrating u to the third du. Right? So my answer here would be u to the fourth over 4 plus c. And of course, when I go back and I make my simple substitution, the final answer would be 2x minus 3 to the fourth over 4 plus c. Okay, let's try example 2. Now, example 2 is a little different because we have an e involved, right? So this is not necessarily a power function. So our focus has to shift a little bit. You say, well, where do I look to find this u? And in a case like this, I think you want to look at the exponent, right? If u is equal to negative 3x, du is equal to negative 3 dx. So the one thing you should note is that the negative 3 and the dx are not literally side by side, but they're in the problem. Because of the commutative property, I could just as easily move this negative 3 to sit right in front of the dx over here, just like it was up here with the 2. So it's okay that it's out in front here, but everything is taken care of. So you can write this equivalently as e to the u du. And of course, this is easy because the integral of e is itself. So e to the u plus c is our answer, but obviously we want to write that appropriately using some of the original expressions that we had. So our final answer is just e to the negative 3x plus c. So this is all well and good, but I think the bigger question is, well, what do I do if this exact derivative is not in the problem? And I think that's what we have to handle next, right? So let's take a look at something maybe like example 5. Okay, so in example 5, again, we have e to this sine 5x, right, times cosine of 5x. Now, as you get a little bit more accustomed to this process, right, you will definitely question yourself in terms of what you're, going to pick for u. Just pick something and derive it and see if it matches up. So if in this case, if I wanted to pick cosine as my u, the derivative of that is negative sine 5x, and that's great that I see a sine 5x, but what about e? Everything has to be accounted for. So again, like we said in the previous example, when you have e in the integrand, usually the exponent for e is going to be where we look. So that's where I'm going to look here, certainly. So u is going to be sine of 5x, and it just so happens that du, now watch this, is cosine of 5x dx, but there's also a 5 involved, right, because of the chain rule. So now we have a little bit of a problem because what I see here, right, I see here, except there's this kind of like this wild card. So if I'm going to make this equivalent substitution, here's kind of what I'm doing. I'm actually solving for this cosine of 5x dx quantity, which means I'm getting this over here. So 1/5 du is equal to cosine of 5x dx. Now you say, well, why would you do that? I'm doing that because I want to be able to make a perfect one-to-one match when I substitute. So now I can do that, and here's why. All right, let's start with the e. Now I made u sine of 5x, so I can write that as e to the u. Cosine of 5x dx can be written as 1/5 du. And the beauty of this is that since 1/5 is a constant, right, this 1/5 could actually swing outside here, and I can look at this problem as 1/5 e to the u du, which again is really easy to deal with. So my answer would just be 1/5 e to the u plus c. Now again, I'll go back and substitute, so 1/5 e to the sine 5x plus c. Now, if you see this pattern, then yes, you can put a 1/5 outside of the integral right away. You don't have to sit there and wait and do all this little smoke and mirrors and moving stuff around, but just wanted to show everybody this is where it comes from. Okay, so to finish up here, here's what we're going to do. I'd like you to take a look at examples 3, 4, 6, 7, right? 3, 4, 6, 7, and then finish up with 12 and 13. Okay, what I'm going to do is get you some answers, but take your time, pause the video, we'll come back, and we'll give you answers to all these, and of course we'll answer questions in class as well. Alrighty, here we go, answer time. So, for number 3, should wind up with negative 1/3 cosine cubed x plus c. For number 4, you should get negative e to the 1 over x plus c. For number 6, you should get 1/49 sine 49x plus c, and we're going to talk about that one in a second. And number 7, you should get negative 2 cosecant pi theta plus c. Let's just diverge for a second and talk about number 6. 6 and 7 are very similar because, again, we have something new here. There's no power function. There's no e. So where do we look for u, right? Well, with trig functions, a lot of times, if the trig function is not raised to a power, then we like to look inside the angle. So we're going to make u 49x here, and du is 49 dx. So you can see I'm off by that 49 constant. So that's where I'm getting the 1/49 from. And then it turns into just cosine of u du, and that's how I'm arriving finally at 1/49 sine of u, which obviously was 49x. So try 7 again. If 6 and 7 gave you trouble, now try 7 again with that same idea in mind. The other thing is at the bottom of the page, you'll see where it says to summarize, where might one look for u? And now we've actually taken 3 different approaches here. One, we've looked at a power function. Let's look at that. All right, so think about that. Where will I look for u when I'm dealing with a power function? We've looked at an exponential function. Where will I look for u there? And we've looked at a trig function. So these are 3 cases we've actually seen now in these couple of examples. I think you need to fill that box in, but if not, really kind of talk with the other people in class outside of class. Get into a group message or that kind of thing, and just talk to people about what we're looking for, that way we can help each other out. Let's give you the final couple answers here for number 12 and 13. Okay, now 12 and 13 I wanted you to do because we're combining the substitution method we're using with the fundamental theorem here. So number 12 should get finally 8 over 105, and number 13 should get 9 over 128. Okay, so in case you're looking for just a little bit of guidance on that, again, we can talk about it. The setup for number 12, u wound up being 30 minus x squared, because you could look at that as something being raised to a negative 2 power. And du here was equal to negative 2x dx, so you were off by a negative 2. So when you set your integral up, you had a negative 1/2 on the outside, and you were integrating u to the negative 2 du. And then for 13, u here was sine of 2t, and du was equal to 2 cosine of 2t. So you're off by a 2 again. So that led us to 1/2 integral u to the 3rd du. Now again, remember at the end of all this you had to plug in. So f of b minus f of a gets you those numerical values. And technically, again, you're just finding the area under the curve from these lower limits to upper limits. So let's talk about the rest of it in class. And don't worry about the other pages not covering the video. We're going to talk about those in class as well.